We're starting right away with a paper called LLMs as Noisy Channels, a Shannon perspective on model capacity and scaling laws. This is from researchers at ByteDance Seed, the University of Virginia, and UC Berkeley.
And honestly, this paper completely shatters the fundamental math that the whole AI industry relies on to train these massive models.
Right, because traditional monotonic scaling laws, specifically the ones from OpenAI and DeepMind's Chinchilla, they're actually failing to explain these U-shaped degradation phenomena.
Exactly, like catastrophic overtraining or, those steep quantization drawbars.
Yeah. So the breakthrough here is that they map LLM training directly to the Shannon-Hartley Theorem for communication over a noisy channel, which proves that scaling your model size or your data without preserving the signal-to-noise ratio mathematically guarantees that performance will degrade.
It's huge. This new Shannon Scaling Law accurately predicts the exact loss basins where the other laws completely collapse. They even successfully extrapolated the performance of a 12 billion parameter Pythia model up to 307 billion tokens using just small-scale data.
Which is just wild. So welcome to this episode of AI Paper Slop. Today, we're doing a deep dive into this source material because, well, it's a total paradigm shift.
Yeah, it really is. If you're managing massive compute clusters, we are finally moving away from just brute force scaling and moving toward a real physics-based understanding of model capacity.
Right, because if you're an ML engineer, you've lived by the scaling is all you need mantra for years now.
Oh, absolutely. Everyone knows the Kaplan and Chinchilla curves by heart at this point.
Right. You scale up your parameters, which we'll call N, and you scale up your tokens, which is D. And the loss curve is just supposed to go in one direction, right? Down.
Monotonically down. That's the assumption.
But if you're actually doing this, you've definitely hit that wall where you throw another terabyte of data at a fine-tuning run, and the model somehow just gets stupider.
Yeah, the loss bottoms out and then just starts creeping right back up.
Exactly. A non-monotonic U-shaped curve. So why do traditional scaling laws fail so hard here?
Well, the physical reality on your training dashboard is basically breaking the mathematical equations we use to predict these runs. A strict power law formulation mathematically cannot produce a curve that goes down and then hooks back up.
It physically can't.
Right. So the community has kind of been in denial or, just applying Band-Aids. And the paper highlights two major areas where this is causing real pain for practitioners. First is what you just mentioned, catastrophic overtraining.
Where you pre-train a model too much and then downstream fine-tuning just falls apart.
Exactly. A team pre-trains excessively, assuming more tokens always equals a smarter foundation. But when they move to supervised fine-tuning, the performance degrades. The model has seen so much data that it actually becomes worse at adapting to a new job.
I've seen teams try to fix this by hacking the old laws. They'll take the Chinchilla equation and just tack on an exponential penalty term to account for the learning rate.
Yeah, perturbation-aware law.
Right, but it feels like, taping a spoiler to a tractor to make it go faster.
That is a great way to put it because it doesn't address the underlying mechanics at all. Tacking on a penalty term, sure, it helps you fit a very narrow set of data points, but it completely fails to capture the intrinsic dynamics of the neural network.
And what's the second failure point they look at?
Quantization-induced degradation, or QDD. So we all want to run massive models on cheap hardware, right?
Right, so we quantize them down to lower bits.
Exactly, and you would logically assume that a 12 billion parameter model, which has learned vastly more nuance, would compress better or at least degrade more gracefully than, say, a 1 billion parameter model.
But the opposite happens.
The exact opposite. Under extreme quantization, the larger, more extensively trained models collapse faster and harder.
Wow. Which means, essentially, we need a fundamentally new equation. Since tacking on penalty terms doesn't work, how does this paper rethink the physics of an LLM?
They do something brilliant. They step completely outside modern deep learning and go back to 1948. They treat the LLM like a radio transmission.
I love this analogy. Think about tuning an old analog radio. You're trying to transmit knowledge like the music from a data set into the model's weights. And the prevailing logic has just been crank up the volume.
Just build a bigger speaker.
Right. Build a bigger speaker, which is your model size, and pump more electricity into it, which is your data. But you can't just crank up the volume to hear the music better if the background static is getting louder at the exact same rate.
Exactly. If you don't manage the signal-to-noise ratio, building a massive speaker just blasts deafening static into the room.
So how do they map this to the Shannon-Weaver model?
Okay, so Quad Shannon formulated channel capacity. The Shannon-Hartley Theorem states that capacity, let's call it C equals bandwidth, B times the base 2 logarithm of 1 plus the signal-to-noise ratio.
C equals B times log base 2 of 1 plus S over N.
That's the 1. And the authors took that exact equation and mapped LLM training variables directly onto it. So bandwidth, B, maps to model size. Specifically, N raised to a fitted exponent, alpha.
Okay, so a larger model with more parameters literally has a wider channel. It can capture more features.
Just like a massive antenna can pick up a wider range of frequencies. Then, signal, S, maps to the knowledge in your training tokens. That's D raised to an exponent, beta.
So pumping more tokens is like increasing the transmission power.
Right. But here is the breakthrough. The denominator, the noise. And this isn't just a static background hum. It comes from 3 dynamic places.
Okay, let's break down the static.
Yeah.
The first one makes total sense to me. Data-induced noise. They formulate it as a constant, D times your token count, D raised to the power of delta. Because, scraping the internet gives you data full of typos, contradictions, semantic garbage.
Exactly. And as you push your token count higher, you aren't just accumulating knowledge, you are aggressively accumulating gradient updates on bad data over millions of steps.
The model just becomes more sensitive to that static.
Yeah, but even if you had a mathematically perfect data set, you still have the second source. Model interaction noise. They formulate this as a constant, C times the product of tokens and parameters, so D times N all raised to gamma.
Wait, why do the model and tokens interacting cause noise?
Because you have to view pre-training as a denoising procedure. At step 0, an LLM is a giant matrix of random weights. Pure noise. As training happens, it's slowly denoised. This interaction term captures the friction of your specific model architecture trying to resolve patterns over time.
Oh, that makes sense. The sheer act of optimizing a massive high-dimensional space generates its own interference.
Right. And the third source is just the irreducible system entropy, a constant term, E. It covers the hard limits of the transformer architecture.
Okay, so we have this beautiful equation for the capacity of an LLM. But, we track test loss, not capacity.
And the math connection there is perfect. Test loss is simply the reciprocal of the LLM's capacity. Loss equals 1 divided by capacity.
Which explains so much. Because early on, capacity is tiny. So small capacity gains equal huge drops in loss.
That's the steep cliff at the start of the curve.
But later, when the channel is saturated, you need exponentially more capacity to drop the loss even a little bit. It naturally asymptotes.
It perfectly captures the shape of a training curve without forcing artificial constants.
But, okay, an elegant equation is just whiteboard math until it meets real data. How did they actually prove this works under extreme stress?
They did extensive validation. They used the Pythia suite from 160 million up to 12 billion parameters, and the OME2 suite up to 32 billion, evaluated on Wikitext2. And they ran 3 distinct perturbation tests.
Let's get into those, because it's easy to fit a curve to a clean run. What happens when we intentionally break things? Test 1 was Gaussian noise, right?
Yeah, they added Gaussian noise directly to the weights based on specific signal-to-noise ratios.
Yeah.
Starting at 40 decibels down to 10 decibels.
And at 40 decibels, everything looks normal.
Standard chinchilla landscape. You scale parameters and tokens, loss goes down. But as you dial the noise down to 10 decibels, this massive loss basin appears.
Like a crater.
Exactly. There's a narrow valley of optimal performance. If you scale past a certain model size or token count, you climb out of the crater and your loss shoots up. At 10 decibels, the OpenAI and Chinchilla laws completely fail.
They just assume the curve keeps going down.
Right, but the Shannon law holds a robust R-squared of 0.9555 on Pythia. It perfectly maps the crater.
Okay, but nobody is intentionally injecting Gaussian static into production models. The second test is the real messy stuff, supervised fine-tuning.
Yes, tested on GSM-8K for math, CQA for QA, and StarCoder. And here, the noise is the learning rate. High learning rate equals more optimization noise.
He's like violently shaking the radio dial while trying to tune it.
Exactly. And at high learning rates, you get capacity collapse. Traditional laws yield completely absurd predictions. For example, on StarCoder, the OpenAI law gives a negative R-squared.
Wait, negative 1.01, right?
Right.
For anyone rusty on stats, a negative R-squared means the model is mathematically worse than just drawing a flat horizontal line through the average and guessing that forever.
It is actively misleading you. Meanwhile, Shannon stays universally superior, averaging over 0.91 R-squared across the data sets.
Incredible. And the third test is quantization. They post-training quantize these models using GPTQ, AWQ, bit sandbytes, and Quanto.
And at aggressive 2-bit quantization, standard laws suffer catastrophic collapse. The OpenAI law drops to an R-squared of around 0.01 with Quanto.
Wow, basically zero predictive power.
Zero. But the Shannon law maintains an incredible 0.9031.
Because of the antenna effect. The 12 billion parameter model is this massive, highly sensitive antenna. When you crush the precision to 2 bits, it just amplifies the static across billions of pathways.
Yes. The model amplifies the intrinsic noise faster than it adds capacity. Shannon mathematically accounts for this.
Okay, so it can fit noisy data, but the holy grail of any scaling law is extrapolation, right? Can we use data from small, cheap runs to accurately predict the behavior of a massive, unseen model?
The authors designed a rigorous joint extrapolation experiment to test exactly that. They fit the law on the 5 smallest Pythia models using only their first 180 billion tokens or less.
So it's blind to the 12 billion parameter model and blind to the rest of the token budget.
Completely blind. Then they tasked it to predict the 12 billion model on budgets up to 307 billion tokens.
And if you get this wrong in real life, you waste millions of dollars in compute. How did it do?
The 9-parameter full Shannon law achieved an astonishing pooled R-squared of 0.847.
Oh, wow.
While Chinchilla degraded to 0.305, and OpenAI fell to negative 0.082.
Okay, wait, I have to play skeptic here. A 9-parameter law. That sounds like a massive overfitting risk if you only have a little bit of data.
It is a risk, and the authors are transparent about that. They actually provide a simplified 6-parameter version of the law, too. Here's the practical guideline for ML engineers listening. If you are doing single-axis extrapolation, like just scaling up tokens for a fixed model, use the 6-parameter version.
To avoid overfitting.
Right. But you absolutely need the 9-parameter version for joint extrapolation, where you scale N and D together.
Because of that interaction noise term?
Exactly. The C times D times N to the gamma term. Without modeling the interaction between tokens and parameters, the law drops drastically in high-noise environments.
That makes total sense. So looking at those exponents, alpha, beta, gamma, delta, what is the mathematical proof that simply scaling up is eventually doomed?
Table 9 in the paper shows 2 major kind of bitter truths. First, model scaling backfires. In clean, high SNR regimes, bandwidth, which is alpha, outpaces model noise, which is gamma.
More signal than noise.
But under heavy perturbation, it inverts. Gamma becomes greater than alpha. This proves that beyond a certain threshold, scaling up model size N amplifies intrinsic noise faster than it adds capacity.
The massive antenna chokes on the static.
Exactly. And the second truth is even crazier. Token noise always wins. The exponent for data noise, delta, persistently exceeds the signal exponent, beta, across all scenarios.
Wait, really? Even in clean pre-training runs?
Even in clean pre-training, delta is always greater than beta.
So if we think about that for a second, if the data noise exponent delta will always mathematically overshadow the signal exponent beta, then U-shaped degradation isn't just some bug caused by bad quantization.
No, it's an intrinsic limit of LLMs.
That is profound. If accumulating tokens eventually guarantees a noise takeover, maybe the next era of AI isn't about hoarding the biggest data sets on the internet. Maybe it's about radically filtering for information density to maximize the signal-to-noise ratio before we even start training.
It really reframes everything we are doing with data right now.
Absolutely. Well, that wraps up our deep dive into the source material for this episode of AI Paper Slop. If you are prepping the compute budget for your next scaling run, definitely pull up this paper and check out the equations. It might just save you from driving your model into a loss basin. Thanks for listening.